Hello, my name is Shaofeng. In this talk, I'm going to introduce an adaptive relation modeling network tailored for structured data. This is the outline of this talk. I will firstly introduce the specific data type that we are interested in, namely the structured data. And then we formally describe the learning problem of the structured data. In particular, we will focus on neural networks and the limitations of applying conventional neural network models to structured data learning. We then introduce the key observations and ideas for the structured data learning problem and propose our solution by designing a novel neural network model, AMNet, to address the challenges via adaptive relation modeling. We will show some empirical results on several real-world applications to demonstrate the effectiveness and functionalities of the proposed new model. And finally, we will introduce a lightweight framework ARMOR based on AMNet for structured data analytics. Now let's first look at the data part. So structured data, also known as relational data or tabular data, refers to the type of data that can be organized into tables of rows and columns. We show the correspondence of relevant terminology between data management and the machine learning community on the left table. So each row is a tuple or record that corresponds to a specific data sample. And each column or field attribute conforms to a domain of certain constraints and corresponds to a specific feature for the learning model. Structured data is typically stored in a series of tables or relations, and these tables are linked to each other via foreign key attributes. Nowadays, a large fraction of organizations and business store their data in structured data format. And relational databases are the de facto standard for storing and querying structured data, which are critical to their daily operation. Example applications include e-commerce, healthcare, and banking. So right-hand side gives an e-commerce example, which stores the business data of a company into 3 tables of product, order, and customer, respectively. Now let's formally introduce the structured data learning problem. So the input data for structured data learning can be viewed as one logical table of n rows and m columns, which can be extracted from relational databases via core relational operation, for example, projection, join, and aggregation of relevant tables in the database. The logical table abstraction can be achieved by, for example, collecting relevant features on the fly or via the abstraction of multi-table view. Right-hand side illustrates the example logical table extracted from the 3 corresponding tables of the previous e-commerce example, which contains 5 attribute columns. Functional dependency. Formally, from the perspective of relational database, the learning problem of structured data is to model the functional dependency of the dependent attribute y on the determinant attributes x, namely a predictive function f from x to y, where x is typically called the feature vector and y is the prediction target. Let us take the e-commerce data, for example. Suppose the company would like to make a prediction about monthly sales. In this case, the determinant attributes are the month, region, store, and product, and the prediction target is the total sales. Now let's take a closer look at the structured data learning. So the central problem to structured data learning is actually how can we effectively model the feature interactions among attributes? Let us consider the e-commerce example again. In such real-world applications, the correlations and dependencies among attributes are very important for the prediction. For example, in this case, a particular store A may perform better at selling a particular product A, and the stores may push a particular product B in June and in region Avenue 5. So to make accurate sales prediction, the modeling process needs to take into account of all such relevant feature interactions. Cross features. The feature interaction can be mathematically described by the cross feature, which is formally defined in the general form here. That is the product of input features with their respective interaction weights. Specifically, the interaction weight Wi determines the contribution of the ith feature to the cross feature. And Wi equals 0 will max out the corresponding feature Xi in the interaction. And the interaction order of a cross feature refers to the number of non-zero interaction weights, namely how many constituent attributes in the interaction. Neural networks. So we know that neural networks are universal approximator, and theoretically, a single layer neural network is able to approximate any continuous function given enough data and capacity. However, being able to approximate something is not the same as being able to represent it. In particular, the feature captured by each neuron in the neural network is only additive, which simply aggregates input features that are linearly scaled by corresponding weights. And because of this, prohibitively large models are needed to approximate the multiplicative interaction of cross features. And further, implicit modeling with a conventional neural network is also hard to be interpreted. So in this work, we aim to fully exploit the strong modeling capacity of neural networks. And at the same time, we will design a model that is also easy to compute and more interpretable for structured data learning. To achieve this, we propose adaptive relation modeling. So our key observations for relational modeling are that, firstly, explicit modeling cross features is advantageous. This is a preferred alternative to implicit modeling with neural network models, which will be more effective and interpretable. However, one major problem of explicit modeling is that the number of possible cross features is exponentially large. To make the modeling process more efficient and effective, the central problem is then how can we identify the right set of constituent features and also determine the right interaction weights dynamically. This brings us the second key observation, that is, selective and dynamic cross-feature modeling is beneficial. This is because in real-world data modeling, not all input features are useful, and modeling with irrelevant features could simply introduce noise to the features that we want to capture. And based on these two observations, we propose adaptive relation modeling for structured data learning by explicitly capturing cross features on the fly condition on the input. As compared with existing static modeling methods, the constituent features of our cross features are selectively and dynamically determined, which is more parameter efficient and effective. In this slide, we will select and construct novel components and mechanisms for such adaptive relation modeling. In particular, we propose novel exponential neurons and a gated attention mechanism, which we will introduce in the following slides. Firstly, the exponential neuron. Let's look at the difference between a neuron and a cross feature, which is illustrated on the right panel. So the main differences are that, firstly, the way how input X is transformed by the weight W, and secondly, how the transformed inputs are merged together. So for a vanilla neuron, the input X are linearly scaled by a respective weight W, and then summed up to produce the output. While for the cross feature, the inputs are transformed with respective weights as the power. That is, each Xi is raised to the power of Wi, and then the transformed inputs are merged via multiplication. To model cross features more efficiently and effectively, we propose the exponential neuron. The exponential neuron is a variant of a conventional neuron. And the main enhancement is that the exponential neuron models input in the exponential space. As shown in the formulation on the left, this is achieved by applying an exponential transformation upon the aggregated inputs. As the second term in the formulation indicates, each exponential transformation can be equivalently understood as follows. First, each exponential neuron transforms input features into the exponential space, and then the transformed inputs are raised to the power of a corresponding interaction weight. And finally, all the transformed inputs are merged via multiplication. So in this way, each exponential neuron can explicitly capture a specific cross feature. And this is easy to compute and meanwhile enhance the modeling capacity of a canonical neural network model. So with the exponential neuron, we are now able to capture cross features explicitly. The next question is then, how can we selectively and dynamically determine the interaction weights conditioned on the input? To achieve this, we further propose the gated attention mechanism. The gated attention mechanism consists of 3 steps. First, bilinear attention alignment, which is to obtain the compatibility score between each exponential neuron and input. And second, recalibration weight computation, which is to calculate the interaction weights dynamically. And finally, the interaction weights are sent to exponential neurons to assemble the cross features adaptively. Now let's look into details of each step. The first step, attention alignment. So to make the gated attention efficient and effective, each exponential neuron is associated with a learnable query vector Q and a value vector V. Note that first each input feature X is transformed into an embedding vector in the pre-processing module. Then the query vector Qj of the jth neuron is used to calculate the compatibility score between the jth neuron and the ith input feature Xi via the bilinear attention alignment. That is the QJWXI here. So with attention alignment, the compatibility score dynamically captures the relative importance of feature Xi to neuron J. And then the second step, sparse gating. To make each neuron only attend to informative input features, the crux here is to apply alpha ant max on the compatibility score Zj. Alpha ant max is a sparse version of softmax, which can filter out less important inputs. With sparse gating, we can then obtain sparse compatibility score Zj bar. So during training, the value vector Vj here will learn and encode the global importance of different input features for the jth neuron. And the compatibility scores will be used to dynamically gate this value vector for adaptive relation modeling. And the final step, exponential neuron with gated attention. After the sparse gating, we dynamically obtain the interaction weights Wj, which are finally sent to the corresponding exponential neuron to assemble the cross feature. The right figure illustrates how an exponential neuron dynamically assemble a cross feature, where the product is B and the month is June for the interaction between product and month attributes. In this case, all other attributes are filtered dynamically. So with adaptive relation modeling, we can now design a more efficient, effective, and interpretable neural network model called AMNET for structured data modeling. AMNET comprises 3 main modules. First, the pre-processing module, which pre-processes each input feature into an embedding vector for both numerical and categorical features. And second, the adaptive relation modeling module, namely ARM module, which is the core module of the architecture, This module is based on the exponential neuron and gated attention. Note that we adopt the multi-head attention mechanisms with k different sets of bilinear attention weights to model interactions from different representation spaces. And finally, a prediction module, which takes the relational representations from exponential neuron as input and produce model outputs with an MLP for downstream prediction tasks. With AMNet, we can now explicitly model cross features for structured data learning. Next, we briefly discuss the effectiveness, efficiency, and interpretability of AMNet. First, effectiveness. As we discussed previously, explicit modeling cross features is advantageous, and adaptive relation modeling can dynamically filter noisy features, which is more effective than static modeling approaches. In addition, each exponential neuron captures a specific cross feature of arbitrary orders and could potentially represent any combination of interaction features. Therefore, AMNet can generally achieve better prediction performance than existing models. And second, efficiency. All the computation in AMNet can be vectorized and efficiently computed via matrix multiplication, and the complexity is linear to the number of input features and neurons, which is scalable to larger data sets. Also, with exponential neurons, we can now dynamically assemble useful features to reduce redundant features, which is more parameter efficient. And thirdly, the multi-head attention can be parallelized by computing each head in a distributed manner for a higher inference efficiency. And lastly, interpretability. The interpretability of a prediction model is another issue of concern in the model deployment for real-world applications. With the adaptive relation modeling, we can now have a more interpretable modeling process. AMNet provides feature attribution on input features by showing their feature importance in the prediction in both the global and local level. Specifically, AMNet can provide the following interpretation functionalities. First, global interpretability. Specifically, each exponential neuron has a value vector, and it encodes the interaction weights globally over the whole data set. Therefore, the value indicates the relative global importance of each input feature for the corresponding neuron. So we can aggregate these importance values over exponential neurons to obtain global feature importance. And second, local interpretability. With runtime gated attention, we dynamically recalibrate interaction weights via bilinear attention alignment. So these weights encode local feature importance for each input instance dynamically. We can therefore also aggregate these runtime interaction weights to obtain local feature importance. And third, feature interaction term. Finally, we can also have direct access to the cross-feature terms captured by exponential neuron to discover useful feature interactions. So we evaluate AMNet in several real-world applications, including app recommendation, movie recommendation, click-through rate prediction, and healthcare analytics. The baseline model includes 5 categories of models, namely the linear model, second and higher order cross-feature modeling models, neural network-based models, including vanilla neural networks, and also graph neural networks. And finally, various single models ensembled with a neural network. We adopt the same training settings for different models and report both AUC and their parameter sizes. The main results are summarized in the right table. The main findings are that first, higher order models generally achieve better prediction performance, which shows that higher order cross features are indeed essential for relation modeling. And second, AMNet significantly outperforms baseline models, which verifies the effectiveness of modeling cross features in an adaptive and data-driven manner. And third, neural network-based models are still very strong baseline. They generally achieve high prediction performance, while their performance is not as good and as consistent as our ARMNet. Fourth, we can also find that models ensembled with a neural network consistently improve their prediction performance, which suggests that explicit modeling methods are complementary to implicit modeling with a neural network, and their combination can further improve prediction performance. And therefore we augment the modeling capacity of ARMNet with a neural network, and together the ARMNet Plus achieve our best prediction performance. Here we also briefly introduce the interpretation functionalities with ARMNet and demonstrate how ARMNet can provide both global interpretation and local interpretation. We mainly demonstrate with the app recommendation dataset FRAPI and Diabetes 130, which collects 10 years diabetes encounters at 130 hospitals. The task is inpatient readmission prediction. So for global interpretability, we show how ARMNet can identify global interaction terms and support global feature attribution. First, global interaction terms. In the right table, we show the most frequently used cross features globally, which reveal important features, interactions for inspection and deriving insights. So with these interaction terms, we can know which features are highly correlated and important for the prediction. And second, global feature attribution. In the right figure, we show the global feature importance produced by ARMNet on the two data sets. We compare the importance weights by ARMNet with two model agnostic interpretation methods, namely line and sharp. We can notice that the feature attribution is consistent with the two popular interpretation methods. For local interpretability, we show how ARMNet can produce feature importance for each input instance dynamically. The left figure illustrates the local feature attribution for a specific patient. For the from the last row, you can observe that the last 5 features are the most important features for the readmission prediction. And on the right panel, we also illustrate the local interpretation results of the two interpretation methods on the same patient, which basically shows similar results as our ARMNet. So these interpretation results confirm that ARMNet can inherently identify important features used in the relation modeling without resorting to external interpretation methods. In summary, this is the overview of a lightweight analytic framework ARMOR based on ARMNet for relational analytics. During model training, ARMNet is trained to model feature interactions in a selective and dynamic manner. Then during model inference, given the input tuple, ARMOR supports key functionalities, including prediction, global interpretation, and the local interpretability for various structured data analytics. And with that, I'd like to end this talk. Thank you.